You hold a simple light switch in your hand. Flick it up, and the room floods with light. Flick it down, and darkness returns. Simple right, a binary system on or off. But what if I told you that at the heart of that seemingly simple act, a reality far stranger than this exists? A reality where the rules are not so clear-cut, where things can be both on and off, here and there, all at the same time. Welcome to the world of quantum physics. Imagine a universe where a single particle can exist in multiple places at once, a bit like a mischievous sprite flitting between different rooms in your house before you can even catch sight of it. This isn't science fiction. This is the bewildering reality revealed by quantum mechanics, the study of the universe at its most fundamental level. It's a world where the very act of observing something changes it, a bit like trying to measure water in a river as it flows relentlessly to the sea. You always get a slightly different measure depending on when you take it. It sounds incredible, even fantastical, a world Einstein himself famously called spooky. But the strangeness doesn't stop there. Think about your phone, that sleek piece of technology in your pocket. It uses processes which rely on these quantum principles, the same rules which govern the smallest particles in the cosmos. Everything from your GPS tracking your location to the MRI machine allowing doctors to see inside your body depends on a deep understanding of quantum mechanics. This journey will unveil the astonishing secrets of quantum physics, from its mind-bending concepts to its revolutionary technological applications. You'll encounter superposition, the remarkable ability of particles to exist in multiple states simultaneously. Entanglement, a phenomenon where two particles become mysteriously linked, no matter the distance between them. And the profound implications of the observer effect. We will follow the path laid out by pioneering scientists exploring groundbreaking experiments like the double slit experiment, and pondering the philosophical implications raised by Schrödinger's famous thought experiment. Along the way, we'll break down complicated concepts into digestible pieces using analogies to make the seemingly impossible comprehensible. Are you ready to take this quantum leap into the unknown? You see the world as a tapestry of colors, shapes, and textures. You feel the solidity of a table beneath your hand, the smoothness of a glass, the warmth of the sun on your skin. But this is only the surface, a macroscopic view of reality. To truly understand the universe, you must venture beyond what your senses perceive into a realm far smaller, far stranger, the subatomic world. Imagine shrinking yourself down smaller and smaller until atoms become the size of houses. You now see these structures complex and dynamic, dancing and vibrating with incredible energy. Electrons whiz around their nucleus like planets orbiting a star, while protons and neutrons, tiny particles themselves, occupy the center. But even these fundamental building blocks of matter are not solid, impenetrable entities. Instead, they exist as probabilities and energies. Think of a blurry photograph where the subject's precise location isn't definite, but more likely somewhere within a fuzzy region. That's a very close analogy to how things appear at a truly subatomic level. Our everyday experience is utterly macroscopic. It represents a vast simplification of the complexity underneath. The seemingly solid table under your hand is mostly empty space, a vast ocean where particles whiz around, governed by laws that seem to follow a set of rules quite different from those in our everyday world. This is where quantum mechanics truly begins to reshape our understanding of the universe. As you move deeper, your classical view begins to fracture, replaced by the fascinating and often bewildering realities of quantum superposition, a concept previously explored, and the observer effect. This journey into the subatomic realm isn't merely an academic exercise. The technology you use every day, from the computer on your desk to the smartphone in your pocket, depends on an intimate understanding of these quantum principles. These seemingly small particles behaving in ways that seem both wonderfully bizarre and incredibly elegant are the hidden architecture of the tools which power our current technology and are at the center of revolutionary technological advancements yet to come. We'll explore how these principles govern processes ranging from lasers that scan barcodes to the MRI machine, which helps doctors understand and treat illnesses. Prepare to shed your everyday perceptions and step into the realm of possibilities where reality is constantly shifting and reforming before our very eyes. You've glimpsed the subatomic world, a realm where the familiar rules of classical physics begin to crumble. In the world, you experience daily objects have definite locations and predictable behaviors. A ball thrown into the air follows a clear trajectory determined by gravity and initial velocity. A light switch is either on or off. These are the principles of classical mechanics, a physics paradigm that has served us well for centuries. But this seemingly dependable model falters when applied to the quantum realm. Imagine that same ball now shrunk to the size of an electron. Its path becomes uncertain, probabilistic, almost as if it's exploring multiple paths simultaneously. It is not a clear and predictable trajectory. Rather, it is a complex web of potentialities. This is where the counterintuitive nature of quantum mechanics comes into full view. You are facing a different set of rules. In the classical world, things are either one way or another. In the quantum world, things can be both at once. This isn't merely a matter of imprecise measurement, it's a fundamental property of reality at the quantum level. Remember superposition. It is the principle which states that a quantum particle can occupy multiple states simultaneously until it is measured, at which point it collapses into a single definite state. The act of observing, of measuring, forces a decision upon reality. This is a core element of the observer effect discussed in the previous chapter. This stark contrast between the predictable nature of classical physics and the probabilistic nature of quantum mechanics is not a matter of simple scale. It represents a fundamental shift in our understanding of how reality operates. The consequences of this paradigm shift are vast and far-reaching, extending far beyond the theoretical world of physicists. It is the foundation of technologies you interact with daily, as discussed in the first chapter, such as lasers and computer chips, and is set to underpin the next technological revolution involving quantum computing. You stand at a crossroads, bridging the gap between the familiar world of classical physics and the strange new universe of quantum mechanics. The very concepts that once seemed paradoxical are now changing how we see everything, from the deepest workings of the cosmos to the most powerful computers at our fingertips. Prepare to embrace the unexpected. You've learned that the familiar laws of classical physics break down at the subatomic level, replaced by a probabilistic reality. Now prepare to encounter one of the most mind-bending concepts in quantum mechanics: superposition. Imagine a coin spinning in the air. Before it lands, it exists in a state of both heads and tails simultaneously. It isn't simply that we don't know which side is up. It's that both possibilities coexist. Only when the coin lands does it collapse into a definite state, heads or tails. A quantum particle behaves much the same way. Consider an electron, for instance. In the classical world, it would occupy a specific location at any given time. But in the quantum realm, it exists as a wave of probabilities. It's not in one place or another. It's in all possible places at once, a bit like a ghost that can occupy many places at the same time, only manifesting when it interacts. This bizarre behavior isn't limited to position. It extends to other properties such as spin and momentum. The electron exists in a superposition of all possible states until it's measured or interacts with its environment, causing it to choose a single state. This is not merely a theoretical construct. Countless experiments have verified this phenomenon. It's not an issue of limitations with our measurement tools. Superposition is a fundamental property of quantum particles. Think of a fog cloud spreading out. It does not occupy a specific point, but covers many locations at once. It is only when the fog condenses that it settles into a specific area. Superposition is similar. This wave of probability only collapses into a definite state when you observe the particle, an illustration of the observer effect, and what it means to interact with quantum reality. This concept that a single particle can simultaneously exist in multiple states challenges our very understanding of reality. It's a world where possibilities coexist until an interaction, a measurement, forces a decision on the universe. And as you'll soon discover, this has implications far beyond the realm of theoretical physics. You've witnessed the bizarre dance of superposition, where a particle exists in multiple states at once. But the story takes an even stranger turn when we consider the role of observation. This isn't just about a scientist peering through a microscope. It's about any interaction that forces a quantum system to choose a single state. Recall the spinning coin analogy. The coin exists in a superposition of both heads and tails until it lands. Similarly, a quantum particle exists in a superposition of all possible states until it interacts with its environment or is measured. This interaction collapses the superposition, causing the particle to decide on a single state. This is the observer effect. The act of observing changes what is observed. This isn't about a conscious observer influencing the outcome. It's about any interaction. A photon striking a particle, a detector registering its position, any interaction forces the particle to choose. The very act of measurement itself, an interaction, alters the quantum system's behavior. It's a bit like trying to photograph a hummingbird in flight. Your attempt to capture a specific moment alters the bird's behavior, making it impossible to capture a perfectly natural image. You can never fully separate yourself from the system you wish to observe at the quantum level. This seems counterintuitive to our everyday experience. In the macroscopic world, our observations generally don't affect what we're observing. We can watch a ball fall without changing its trajectory. But at the quantum level, the very act of measurement becomes an integral part of the experiment's outcome, changing reality. This blurring of the line between the observer and the observed is central to quantum mechanics. It raises profound philosophical questions about the nature of reality itself and has implications for how we view scientific inquiry. Think about it. If the very act of observation changes the thing being observed, what does this imply about the nature of objective reality? Does reality truly exist independently of our interactions with it? Or is it actively shaped by our presence? This profound realization that the observer is not separate from the observed at the quantum level leads us closer to understanding the fundamental fabric of our universe. You might think quantum physics is confined to the theoretical realm, a subject for scientists in white coats debating complex equations. But you'd be wrong. Quantum mechanics isn't just a fascinating intellectual pursuit. It's the engine that drives much of modern technology. The seemingly esoteric concepts you've explored thus far, superposition, entanglement, and the observer effect, aren't abstract ideas. They are the hidden architecture underlying many of the devices you use every day. Consider the laser pointer you might use for presentations. Its intense focused beam of light is a direct consequence of quantum principles, specifically the stimulated emission of photons, a process governed by the quantum nature of light itself. Lasers are now ubiquitous scanning barcodes performing delicate surgeries and enabling countless other applications, all thanks to our understanding of quantum mechanics. Or think about your smartphone, that pocket-sized marvel of computing power. At the heart of its intricate circuitry are transistors' tiny switches that control the flow of electricity. These transistors rely on quantum mechanical effects to operate efficiently. They wouldn't function the way they do without a deep understanding of quantum phenomena. You interact with these effects many times every day without even realizing it. This technological reliance on quantum mechanics isn't simply a matter of chance, but reflects a fundamental shift in the application of these principles. Medical imaging technologies also owe a substantial debt to quantum mechanics. Magnetic resonance. Imaging, or MRI, for example, utilizes the quantum properties of atomic nuclei to produce detailed images of the human body, assisting doctors in the diagnosis and treatment of illnesses. The same is true for many other technologies, such as atomic clocks, that provide incredibly precise timekeeping for navigation systems. These examples demonstrate that quantum mechanics is not limited to theoretical discussions. Its principles are interwoven into the fabric of modern society, making life as you know it possible. But this is only the beginning. The potential of quantum mechanics is far from fully explored. In the following chapters, you will discover how these quantum principles could revolutionize computing cryptography and many more areas transforming our world in ways we can barely imagine today. You've explored superposition, the observer effect, and the probabilistic nature of the quantum world. Now prepare to encounter one of the most perplexing aspects of quantum mechanics, the dual nature of the electron. In the classical world, objects are either particles or waves. A ball is a particle. A sound wave is a wave. The two are distinct and mutually exclusive. But the electron, a fundamental building block of matter, defies this simple categorization. Sometimes it behaves like a particle, a tiny localized entity. Other times it behaves like a wave spreading out and exhibiting interference patterns. Imagine throwing a handful of pebbles at a wall with two slits. You'd expect to see two distinct piles of pebbles behind the slits. Now imagine replacing the pebbles with waves ripples in a pond, for instance. The waves pass through both slits simultaneously, creating an interference pattern on the other side, a series of alternating bands of high and low intensity. This is wave behavior, a characteristic quite different from that of discrete particles. Remarkably, electrons exhibit both behaviors. In some experiments, they act like particles traveling in straight lines and impacting a screen at discrete points. In others, such as the famous double-slit experiment, they create interference patterns characteristic of waves. The electron isn't simply a particle behaving sometimes like a wave. It fundamentally is both a particle and a wave simultaneously, a concept known as wave-particle duality. This duality isn't a matter of our inability to precisely measure the electron's properties. It's a fundamental characteristic that challenges our classical understanding of reality. It's a bit like an optical illusion that appears as two distinct images, but is one single object where both natures are fundamentally inherent in its very existence. This seemingly paradoxical behavior of the electron underlies many of the quantum phenomena you've already encountered, including superposition and the observer effect, and it provides further confirmation that the universe at the quantum level operates under a different set of rules. This realization that the electron has a dual nature pushes the boundaries of our intuitive understanding, setting the stage for even more perplexing concepts in quantum mechanics. You've learned about the wave-particle duality of the electron. Now let's delve into the experiment that most vividly demonstrates this paradoxical nature, the double-slit experiment. Imagine a screen with two narrow slits. If you fire a stream of particles, tiny marbles, for instance, at this screen, you'd expect to see two distinct bands of impacts on a detector screen behind the slits corresponding to the two openings. Simple, predictable. This is what classical physics would predict. But replace those marbles with electrons. You might expect a similar pattern. However, what you observe is quite different. Instead of two distinct bands, you see an interference pattern, a series of alternating bright and dark bands. This pattern is the signature of a wave, where the wave crests and troughs interfere with each other, creating areas of constructive and destructive interference. The electron acting as a wave passes through both slits, simultaneously interfering with itself on the other side. This confirms the wave nature of the electron. Remarkable in itself, but it gets even stranger. Now let's add a detector to the experiment. This detector's purpose is simple. It's there to monitor which slit each electron passes through. Logically, this should not change the outcome of the experiment, and if anything, just provide extra data. The electrons are still electrons. They are still being fired at the screen. The presence of the detector should have no bearing on the nature of the electrons, so we should still expect to see wave patterns. However, the moment you attempt to observe which slit each electron passes through the interference pattern, disappears. The electrons now behave as if they only went through one slit or the other, producing two distinct bands of impacts on the detector screen, the pattern expected for particles. The act of observation of measuring has fundamentally altered the outcome of the experiment, forcing the electron to choose a single path. The double-slit experiment is more than a curious phenomenon. It's a fundamental demonstration of quantum mechanics, which highlights the wave-particle duality of electrons and the crucial role of observation in shaping quantum reality. The experiment serves as a striking example of the counterintuitive and perplexing nature of the quantum world. It forces a re-evaluation of our fundamental assumptions about reality and how we understand physical laws. You've seen how a quantum particle, like an electron, can exist in a superposition of multiple states, a blurry mix of possibilities. But what happens when we try to pin down its properties? What happens when we observe it? Remember the double-slit experiment. When electrons passed through the slits without being observed, they created an interference pattern behaving like waves. But the moment we added a detector to observe which slit each electron passed through, the interference pattern vanished, and the electrons behaved like particles. The act of measurement forced the wave function to collapse into a single definite state. This isn't just about conscious observation. It's about any interaction that forces the quantum system to choose a single state from the superposition of possibilities. The impact of a photon, the registration of a detector, even the slight interaction of the quantum system with its environment, all of these interactions force a particle out of its indeterminate state and into a definite one. Think of it as a sudden condensation of a fog. The fog's location becomes specific only when it interacts with the world around it. The collapse of superposition isn't a gradual process, it's instantaneous. One moment the particle exists in a probabilistic blend of multiple states. The next it's settled into a single definite state. This abrupt change is a direct consequence of the interaction, the measurement. The seemingly chaotic nature of this sudden collapse highlights the profound difference between the quantum world and our everyday macroscopic experience. This concept, sometimes described as the collapse of the wave function, is a cornerstone of quantum mechanics. It underscores the profound interconnectedness between the observer and the observed, reminding us that the act of measurement is not a passive observation, but an active participant in shaping quantum reality. It is a reminder that the universe is not simply out there, but co-created through our interactions. And this leads us to even deeper questions about the nature of reality and the limitations of our understanding. The collapse of superposition is not just a theoretical curiosity. It has far-reaching implications for our understanding of the universe and our ability to harness the power of quantum mechanics. You've witnessed the observer effect firsthand, the seemingly paradoxical notion that the act of observing a quantum system alters its behavior. This isn't simply a technical detail. It raises profound philosophical questions about the nature of reality. In the classical world, we assume an objective reality exists independently of our observations. A tree falls in the forest, and it makes a sound whether or not anyone is there to hear it. But quantum mechanics challenges this assumption. At the quantum level, the act of observing, of interacting with a system, fundamentally changes its state. This calls into question the very notion of objective reality. Consider the double slit experiment again. The electron's behavior shifts dramatically depending on whether or not we're observing them. Does this mean reality is somehow constructed by the observer? Does the act of measurement bring a particle into existence rather than simply measuring its pre-existing state? These questions have occupied physicists and philosophers for decades, and there is no single agreed-upon answer yet. Some interpret the observer effect as suggesting a form of participatory reality, where the observer is an active participant in shaping the universe rather than a passive observer. This perspective suggests that the universe isn't a fixed, predetermined entity, but one that evolves and changes in response to our interactions with it. Others argue that a more nuanced view is required, recognizing that the act of observation or interaction merely reveals properties of the quantum system that were pre-existing, even if the system is described by probabilities rather than certainties. The observer's paradox highlights the limitations of our classical intuition when applied to the quantum world. It forces us to confront the profound mystery of how our understanding interacts with the world around us, not just as scientists making observations, but as conscious beings experiencing the universe. The consequences of this paradox extend beyond the laboratory, touching upon fundamental questions about consciousness, free will, and the very nature of existence. The observer effect isn't simply a scientific puzzle. It's a philosophical enigma that pushes us to reconsider our place within the universe and the limits of our own perceptions. You've explored superposition and the observer effect, witnessing how the act of observation can fundamentally alter a quantum system. Now let's consider a thought experiment designed to highlight the strangeness of quantum mechanics, Erwin Schrödinger's cat. Imagine a cat placed inside a sealed box. Along with the cat is a radioactive atom, a Geiger counter, and a vial of poison gas. The atom has a 50% chance of decaying within an hour. If it decays, the Geiger counter detects it, triggering a mechanism that breaks the vial, releasing the poison gas, killing the cat. If the atom doesn't decay, the cat remains alive. According to quantum mechanics, the atom exists in a superposition of both decayed and undecayed states until it's observed. Therefore, the cat's fate is linked to the atom's state. Until we open the box and observe the system, the cat, too, exists in a superposition both alive and dead simultaneously. This is, of course, absurd from a macroscopic perspective. You don't expect to find a cat in a state of being both alive and dead. The paradox highlights the inherent tension between the quantum world, where superposition is commonplace, and our everyday experience. Schrödinger's thought experiment was designed to illustrate the absurdity of applying quantum principles directly to the macroscopic world, but the paradox also forces us to confront fundamental questions about the observer effect and the nature of measurement. The cat paradox isn't a literal experiment. It's a thought experiment used to clarify or challenge the implications of quantum mechanics. until the box is opened and the system observed both the atom and the cat exist in a superposition of states. The moment the box is opened and the system interacts with the outside world, the superposition collapses, forcing a definite outcome, a live cat or a dead cat. This thought experiment, whilst seemingly bizarre, beautifully encapsulates the counterintuitive nature of quantum mechanics. Schrödinger's cat serves as a stark reminder of the limitations of applying classical intuition to the quantum realm, showcasing how the principles of quantum mechanics generate seemingly impossible situations when applied to larger systems. Schrödinger's cat, though a thought experiment, forces us to confront the unsettling implications of quantum mechanics for our understanding of reality. The seemingly absurd scenario, a cat existing in a superposition of both alive and dead states, highlights the conflict between the quantum world and our macroscopic experience. The paradox lies in the fact that the cat's fate is inextricably linked to the quantum state of the radioactive atom. Until the box is opened and the system is observed, both the atom and the cat exist in a superposition of states. This is a direct consequence of the observer effect and the collapse of the wave function discussed in previous chapters. The act of observation, or any interaction, forces a definite outcome. The strangeness of Schrödinger's cat stems from our intuitive understanding of reality. In our everyday world, things are either one way or another. A cat is either alive or dead. There's no in-between. However, quantum mechanics suggests that at the subatomic level, such definite states don't always exist. Probabilities and potentialities reign supreme until an interaction forces a definite outcome. While Schrödinger's cat highlights the inherent strangeness of applying quantum principles to macroscopic objects, its implications run much deeper. It challenges our classical intuitions about the nature of reality itself. Does objective reality exist independently of the observer, or is it shaped by the act of observation? The answer remains elusive, sparking ongoing debate among physicists and philosophers alike. This lack of a definite answer does not negate the validity of the theory. It merely emphasizes the counterintuitive and mind-bending nature of the quantum world. The cat paradox isn't just a cute thought experiment. It serves as a powerful illustration of the profound challenges quantum mechanics poses to our understanding of reality, forcing us to confront the limitations of our classical worldview and embrace the uncertainties inherent in the quantum realm. You've witnessed the dance of superposition, where a particle exists in all possible states at once, and felt the power of observation collapsing that myriad of possibilities into a singular reality. But prepare yourself for a phenomenon so profound, so utterly baffling, that Albert Einstein himself famously dubbed it the spooky action at a distance. This is quantum entanglement. Imagine two coins. You toss them, and before they land, each is in a state of superposition, both heads and tails simultaneously. If they were classical coins, their outcomes would be independent. One landing heads tells you nothing about the other. But what if these weren't just any coins? What if they were quantum coins? Quantum entanglement occurs when two or more particles become intrinsically linked, no matter how far apart they are. Their fates are intertwined, their properties so deeply connected that they can no longer be described independently. Picture this. Two electrons are created together in a special way, and their spins become entangled. One is spin up, the other is spin down, but until you measure them, each individually exists in a superposition of both spin up and spin down. It's like having two identical locked boxes, each containing a single glove, one left, one right. But you don't know which box holds which glove until you open one. Now imagine these two entangled electrons are separated by an immense distance, perhaps light years apart. One is here on Earth, the other hurtling through the vacuum of space towards a distant galaxy. If you measure the spin of the electron here on Earth and find it to be spin up, then instantly its entangled partner light years away will definitively be spin down. There is no delay, no time for a signal to travel between them, even at the speed of light. The correlation is absolute and immediate. This instantaneous connection is what baffled Einstein and his contemporaries. How could information seemingly travel faster than light, violating the fundamental speed limit of the universe as dictated by his theory of relativity? This wasn't merely a coincidence. It was a profound non-local connection where the measurement of one entangled particle irrevocably determines the state of its distant partner, collapsing its superposition in lockstep with the other. The spooky action stems from this apparent defiance of conventional physics, where influences seem to leap across any distance without a visible bridge. Scientists using increasingly sophisticated experiments over decades have repeatedly confirmed the reality of quantum entanglement. Data from groundbreaking research, such as the experiments led by Alain Aspect in the early 1980s, and more recently by quantum satellite missions like China's MISSIS, have unequivocally demonstrated that entangled particles behave precisely as quantum theory predicts. They solidify this bizarre phenomenon as a cornerstone of our understanding of the universe. These findings rewrite our understanding of locality and causality. Embrace this revelation, for entanglement is not merely a theoretical curiosity. It holds the key to the next generation of technological marvels. It forms the bedrock of quantum computing, promising to solve problems currently impossible, and provides the unhackable security of quantum cryptography. Where quantum physics shines, bright entanglement glows brightest, transforming our grasp of communication and computation. How will this seemingly impossible connection ultimately reshape your understanding of reality's deepest threads? You have grappled with quantum entanglement, that astonishing phenomenon where particles become intimately linked, their destinies intertwined across vast distances. It is this very concept, this instantaneous connection, that truly troubled one of the greatest minds in history, Albert Einstein. He famously described it as the spooky action at a distance, a phrase that encapsulates his profound skepticism about this peculiar aspect of quantum mechanics. For Einstein, a universe governed by his theory of relativity, where nothing could travel faster than the speed of light, this seemed utterly impossible. His classical worldview, rooted in determinism and locality, insisted that physical properties should exist independently of observation, and that any influence between distant objects must travel through space at a finite speed. The idea that measuring one entangled particle could instantaneously influence its partner, no matter the distance, struck him as a direct violation of these deeply held principles. Imagine Einstein's perspective. He believed in a local realism, a universe where objects have definite properties, even when unobserved, and where information cannot travel faster than light. But entanglement presented a direct challenge to both. If two entangled particles, say with opposite spins, are separated by light years, and you measure one to be spin up, the other instantaneously becomes spin down. To Einstein, this implied either that a hidden signal was passing between them faster than light, or that the particles somehow knew what the other would be even before observation, defying the probabilistic nature of quantum mechanics. He argued that quantum mechanics, while successful, must be an incomplete theory, lacking some hidden variables that would explain these correlations in a classically acceptable way. This was no mere philosophical quibble. It was a profound intellectual confrontation at the heart of physics. Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, articulated this challenge in a seminal paper known as the EPR paradox, In 1935, they argued that quantum mechanics, if entanglement was true, implied either non-locality, faster-than-light influence, or a lack of objective reality particles not having definite properties before measurement, neither of which they found acceptable. Their intent was to demonstrate that quantum mechanics had a logical flaw, but decades later, ingenious experiments, most notably those building on the work of physicist John Stuart Bell, began to directly test Einstein's challenge. These experiments, like those pioneered by Alain Aspect in the early 1980s and further refined by missions such as China's MISSIOS satellite, provided compelling evidence that Einstein, for all his brilliance, was mistaken on this point. The spooky action was indeed real. The results consistently favored quantum mechanics, showing that entangled particles do behave in this non-local, instantaneously correlated way, defying the principles of local realism. Einstein's skepticism, while born from a classical understanding, inadvertently pushed the boundaries of scientific inquiry. His challenge forced scientists to devise experiments that ultimately confirmed entanglement, solidifying quantum mechanics as an astonishingly accurate, albeit counterintuitive description of reality. How does it feel to witness such a profound debate, a clash of scientific titans whose legacy continues to shape our understanding of the universe? You have grappled with the perplexing reality of quantum entanglement, that intrinsic link between particles that confounded even Albert Einstein. You understand that these particles, once entangled, share a destiny, their states becoming perfectly correlated, no matter the vast distances that separate them. But how can this be? How do they remain forever linked, communicating instantly, without any known physical medium? The key lies in understanding that entangled particles are not merely two separate entities with some mysterious connection. Instead, they are best described as parts of a single unified quantum system. Their individual properties, like spin, do not exist independently until measured. Before observation, they both exist in a superposition of all possible states, but critically, their collective state is known. Think of it like a pair of shoes. You know you have one left and one right even before you look at them. You don't know which is in which box until you open one, but the pairing is definite. The moment you see one is a left shoe, you instantly know the other is a right shoe, no matter how far apart the boxes are. For entangled particles, their properties are not independently defined until an interaction forces them into a specific state. Their fates are woven together into one shared quantum fabric. So when you measure one entangled particle, you're not sending information to the other. Rather, you are making a joint measurement on a single extended system. The act of measuring one particle instantaneously collapses the shared superposition, defining the state of both particles at once, according to their predetermined correlation. This is why there is no information traveling faster than light. The information wasn't sent. It was already intrinsically linked, waiting to be revealed. This profound unity, this shared wave function that describes the entire entangled system, defies our classical intuition of separateness. It suggests a deeper, more fundamental interconnectedness within the universe at its smallest scales. Experiments such as those conducted by Alain Aspect and the remarkable quantum satellite missions have repeatedly confirmed that this intrinsic link persists even over thousands of kilometers. These findings, gathered through meticulous observations and data analysis, have solidified our understanding that quantum entanglement is not a glitch in the system, but a fundamental aspect of reality. It's a beautiful, if bewildering, ballet of particles forever dancing in lockstep. This unbreakable bond is not just a scientific curiosity, it is the very foundation upon which revolutionary technologies like quantum computing and quantum cryptography are being built. These applications aim to harness this deep interconnectedness, using it to solve problems and secure communications in ways previously unimaginable. As you reflect on this profound unity, this spooky action that is so intimately woven into the fabric of reality, consider how this fundamental connectedness at the quantum level might challenge your perception of individuality in the larger universe. You have now grasped the profound and counterintuitive nature of quantum entanglement, that intrinsic link between particles so powerful it spans any distance. This spooky action at a distance, as Einstein termed it, leads inevitably to one of the most intriguing questions in all of physics: does quantum entanglement allow for faster-than-light communication? At first glance, it certainly seems that way. Imagine two entangled particles separated by a light year of cosmic void. You perform a measurement on the particle here on Earth, and its distant partner a light year away instantly collapses into a correlated state. If you measure your particle's spin to be up, you immediately know its partner's spin is down. This appears to be an instantaneous transfer of information, a clear violation of the cosmic speed limit set by Einstein's theory of relativity. It's a compelling thought, a tantalizing prospect of instantaneous communication across the vastness of space. But here is where the enigma deepens, and the rules of the quantum universe subtly reassert themselves. While the correlation between entangled particles is indeed instantaneous, this does not, in fact, allow for faster-than-light information transfer. You cannot use entanglement to send a message. Think back to the analogy of the paired gloves in two distant boxes. When you open your box and find a left glove, you instantly know the other box holds a right glove. This knowledge is instantaneous. However, you could not choose to put a left glove in your box to signal left to the person with the other box. The outcome of your measurement, whether you find a left or a right glove, is fundamentally random and unpredictable from your perspective. It's determined by the collapse of the shared wave function at the moment of observation. The same principle applies to entangled particles. While their outcomes are perfectly correlated, the specific outcome of any individual measurement remains probabilistic. You cannot force your particle to be spin up or spin down at will. You only discover its state when you measure it. Since you cannot control the outcome of your measurement, you cannot encode a message into that outcome. Therefore, the information you gain is about the shared correlated state of the system, not a message intentionally sent from one point to another. This distinction is crucial. Entanglement reveals a deep, non-local connection, a unified quantum system where parts respond as one, but it does not break the light-speed barrier for transmitting classical information. Data from countless experiments building upon the foundational work that confirmed entanglement consistently reinforces this. The universe holds its secrets close, even as it reveals its most mind-bending truths. The instantaneous knowing is about a shared pre-existing reality, not an active act of faster-than-light messaging. This understanding resolves Einstein's apparent paradox without violating relativity. It demonstrates that while the quantum world operates under rules far stranger than our classical intuition, it remains internally consistent, preserving the fundamental laws of the cosmos. What does this profound distinction reveal about the very definition of communication itself and the limits of what can be truly transmitted? You have navigated the intellectual battlefield where Albert Einstein's classical intuition clashed with the quantum reality of entanglement. You've heard his famous critique, the spooky action at a distance, born from his belief in local realism and the universal speed limit of light. But for all his brilliance, the universe at its most fundamental level often defies classical expectations. The time has come to reveal the undeniable evidence that has transformed entanglement from a puzzling theoretical concept into a confirmed, experimentally verified cornerstone of physics. The story of this confirmation truly begins with physicist John Stuart Bell. Decades after Einstein, Podolsky, and Rosen articulated their paradox, Bell in 1964 devised a brilliant theoretical framework known as Bell's theorem. This theorem provided a way to experimentally test whether the correlations observed in entangled particles could be explained by hidden variables, those unknown local factors Einstein hypothesized, or if they truly represented a non-local quantum phenomenon. Bell's inequalities set a statistical limit. If hidden variables were at play, the correlations between entangled particles would never exceed a certain value. If quantum mechanics was correct, however, the correlations would be stronger, violating Bell's inequalities. Armed with this theoretical guide, scientists embarked on a quest to definitively test entanglement. One of the most pivotal breakthroughs came from the work of Alain Aspect and his team in the early 1980s. Their experiments involved entangled photons, which were sent in opposite directions to detectors. By rapidly changing the measurement settings on the detectors, Aspect's team demonstrated that the correlations between the photons' polarizations consistently violated Bell's inequalities. This was a direct, irrefutable challenge to Einstein's local realism. The particles truly seemed to be linked in a way that defied any classical explanation of hidden information. These initial experiments opened the floodgates for further research. Over decades, scientists refined the techniques, closing various loopholes that skeptics might point to. They increased the distances over which entanglement was confirmed, ensuring that no classical signal could possibly travel between the entangled particles during the measurement time. They ensured the randomness of measurement choices, eliminating any possibility of pre-programming the outcomes. More recently, data from ambitious quantum satellite missions like China's MISSIOUS satellite, launched in 2016, have pushed the boundaries even further. MISSIOUS successfully demonstrated entanglement distribution over distances exceeding 1,200 kilometers between ground stations, then even further to different continents, and later even established quantum key distribution, a direct application of entanglement for secure communication over similar vast distances. These missions provide undeniable real-world evidence of entanglement's persistence across truly cosmic scales, far beyond the confines of a laboratory. These numerous meticulously designed and executed experiments, from groundbreaking research decades ago to cutting-edge missions today, all point to the same conclusion: quantum entanglement is real. It is not an anomaly nor a flaw in quantum theory, but a fundamental characteristic of our universe. The spooky action has been rigorously tested and confirmed, fundamentally reshaping our understanding of locality and causality. It solidifies our grasp on the universe's weirdest rulebook. The evidence is overwhelming. Entanglement is not just a theoretical oddity, it is a verifiable phenomenon, a testament to the profound and often counterintuitive truths revealed by quantum physics. Given this robust experimental confirmation, what new possibilities and challenges do you foresee as humanity continues to embrace these extraordinary quantum phenomena? You live in an age defined by connection, where information flows across the globe at unimaginable speeds. From personal messages to sensitive financial data, from national security secrets to medical records, the security of this information is paramount. But every day, new threats emerge, challenging the encryption methods designed to protect our digital lives. What if there was a way to communicate that was fundamentally unhackable, secured not by complex algorithms, but by the very laws of the universe? Enter quantum communication, a revolutionary field that harnesses the bewildering power of quantum entanglement to create truly impenetrable networks. You've already explored the spooky action at a distance, where entangled particles are forever linked, their fates intertwined even across vast distances. While this connection does not allow for faster-than-light messaging, it offers something far more profound for security: instantaneous, undeniable detection of any eavesdropping. The core technology behind this secure communication is quantum key distribution, or QKD. Imagine you and a friend, separated by continents, want to share a secret encryption key. In classical cryptography, this key could potentially be intercepted and copied without your knowledge. But with QKD, you use entangled particles, often photons of light, to generate this key. Each photon's quantum state, its polarization, for example, can represent a bit of information. Because these photons are entangled, if you measure your photon to be vertical, you know your friend's photon will instantly be horizontal, creating a shared secret sequence. The genius and the unhackable nature comes from the observer effect. Remember how the act of observation fundamentally alters a quantum system. If an eavesdropper attempts to intercept these entangled photons to measure their quantum states, their very act of measurement collapses the superposition and disturbs the entangled link. This disturbance is not subtle. It introduces detectable errors into the quantum key. You and your friend would immediately notice these errors, alerting you that someone has tampered with your communication channel. It's like a secret handshake that changes the moment someone tries to peek. The laws of quantum physics guarantee that the eavesdropper cannot extract information without leaving an undeniable trace. This isn't theoretical conjecture, it's a rapidly developing reality. Data from research missions building on decades of foundational science has repeatedly demonstrated the viability of quantum communication. The Chinese Maisha satellite, for instance, has already conducted groundbreaking experiments establishing quantum key distribution between ground stations over thousands of kilometers. This mission, alongside others worldwide, is actively building the infrastructure for a global quantum internet, pushing the boundaries of secure data exchange far beyond what was previously thought possible. The implications are immense. Quantum communication promises a future where sensitive information from national defense protocols to personal banking details can be transmitted with absolute confidence, protected by the immutable rules of the quantum realm. It's a race against ever more powerful computers that could one day break classical encryption, but quantum security offers a fundamentally different and ultimately more robust defense. As we stand at the precipice of this quantum revolution, how will the promise of truly unhackable communication reshape our concepts of privacy, trust, and global connectivity? You hold in your hand a device of astonishing computational power, your smartphone or computer. These machines process information using bits, tiny switches that are either on or off, representing a 0 or a 1. They perform calculations by manipulating these bits in a sequential step-by-step manner. For all their speed, there are problems of such immense complexity that even the most powerful supercomputers would take longer than the age of the universe to solve. What if there was a way to compute that transcended these limitations, harnessing the deepest, most peculiar rules of reality itself? Enter the quantum computing revolution, a new era of computation, where the very fabric of the universe becomes the engine of processing. This groundbreaking field leverages the principles of quantum mechanics. You've explored superposition and entanglement to achieve computational feats previously unimaginable. Instead of classical bits, quantum computers use qubits, or quantum bits. Unlike a classical bit that must be either 0 or 1, a qubit, thanks to superposition, can exist as 0-1 or both simultaneously. Imagine a light switch that isn't just on or off, but can also exist in a state of being partially on and partially off, or even a blend of both at the same time. This seemingly simple difference unlocks an exponential leap in processing capability. A single qubit can represent two pieces of information at once. 2 qubits can represent 4, 3 can represent 8, and so on. Every additional qubit doubles the processing power, creating an enormous computational space that classical computers simply cannot replicate. The true power emerges when you introduce entanglement. When qubits become entangled, their states are intrinsically linked. This means that manipulating one entangled qubit instantaneously affects the others, allowing a quantum computer to process vast amounts of information in parallel. Where a classical computer would have to test each possible solution one by one, a quantum computer, through superposition and entanglement, can explore many solutions simultaneously, like traversing every path in a complex maze at once. This parallel processing capability is the cornerstone of its revolutionary potential. This isn't just about faster calculations, it's about solving entirely new classes of problems. Imagine discovering new materials with properties tailored at the atomic level, designing drugs with unprecedented precision by accurately modeling molecular interactions or optimizing complex logistical networks for global supply chains. Quantum computers promise to break modern encryption that protects our digital world, a double-edged sword that underscores the urgency of quantum communication as discussed in the previous chapter. They could revolutionize artificial intelligence weather forecasting and our understanding of fundamental physics itself. Scientists and engineers across the globe are diligently working to overcome the formidable challenges of building and maintaining these delicate machines. Qubits are incredibly fragile, prone to decoherence from environmental interference, which causes them to lose their quantum properties. But progress is rapid with data from institutions like IBM and Google consistently demonstrating increasing qubit counts and improved error correction. This is not a distant dream. It is a rapidly approaching reality. The quantum computing revolution stands poised to fundamentally alter our relationship with information and problem-solving, pushing the boundaries of what is computationally possible. How will this unprecedented computational power ultimately transform the world you inhabit? And what new horizons will it open for humanity's greatest challenges? You have journeyed through the fundamental principles of quantum mechanics, from superposition and entanglement to the observer effect and the double-slit experiment. You've witnessed how these seemingly abstract concepts are not confined to theoretical discussions, but are actively shaping our world. We've seen quantum mechanics powering technologies like lasers and transistors, enabling secure communication through quantum key distribution and promising to revolutionize computation with quantum computers. But the story of quantum technology is far from over. It is a rapidly evolving landscape pushing the boundaries of innovation into uncharted territories. Beyond the applications you've explored, quantum mechanics is the bedrock for an array of emerging technologies, each with the potential to transform industries and our daily lives. Quantum sensing, for instance, utilizes the extreme sensitivity of quantum systems to measure physical quantities with unprecedented precision. Imagine devices capable of detecting gravitational waves with astonishing accuracy or magnetic field sensors so sensitive they can map brain activity in real time with unparalleled resolution. Such advancements could revolutionize fields from medicine and geology to navigation and fundamental scientific research. Then there's the burgeoning field of quantum materials. By precisely controlling the quantum states of atoms and electrons, scientists are creating entirely new materials with novel properties. These could lead to superconductors that operate at room temperature, enabling lossless energy transmission, or materials with exotic electronic or optical characteristics that pave the way for next-generation electronics and energy solutions. The possibilities are as vast as the quantum realm itself. The research and development in these areas are accelerating at an extraordinary pace. Governments and private sectors worldwide are investing billions in quantum research, recognizing its potential to drive economic growth and national security. Data from ongoing experiments like those in advanced atomic clocks or quantum simulators consistently demonstrate breakthroughs that push the field forward. These advancements are not isolated incidents, but part of a sustained global effort to harness the full spectrum of quantum phenomena. You stand on the threshold of an era defined by quantum technologies. These innovations promise to unlock solutions to some of humanity's most pressing challenges, from developing new medicines and tackling climate change to securing our digital infrastructure and exploring the very origins of the universe. The journey through quantum physics has revealed a universe far stranger and far more powerful than we ever imagined. As these quantum technologies mature and become integrated into our lives, what unforeseen societal shifts and ethical considerations will emerge? You've journeyed from the subatomic realm to the cutting edge of quantum technology, exploring principles like superposition entanglement and the observer effect. Now let's revisit one of the foundational quantum technologies that has become so ubiquitous you might overlook its profound quantum roots: the laser. Remember the concept of stimulated emission of photons discussed earlier as the quantum principle underlying laser technology. This is where the magic truly happens. Lasers work by exciting atoms in a material like a crystal or a gas to a higher energy state. These excited atoms are like a coiled spring brimming with potential energy. Crucially, these atoms are kept in a state of population inversion, meaning more atoms are in the excited state than in the lower energy state, which is a crucial condition for laser operation. When one atom in this excited state naturally emits a photon, that photon possesses a specific energy and direction. If this photon happens to pass by another atom that is also in the excited state, it can stimulate that atom to emit an identical photon 1 with the same energy phase and direction. This is the essence of stimulated emission. These two photons can then go on to stimulate more atoms, creating a cascade, an avalanche of identical photons. This coherent beam of light is what we recognize as a laser. It's a symphony of photons all marching in step, amplified, and directed. This quantum process allows for the creation of a highly concentrated beam of light that is monochromatic, contains only one wavelength, coherent. All waves are in phase and collimated travels in a straight line with minimal divergence. These properties are what make lasers so versatile and powerful. You encounter them every day in the barcode scanner at the grocery store, the precise cutting and welding tools in manufacturing the fiber optic cables, transmitting data across the globe at breathtaking speeds, and even in the delicate procedures of eye surgery. The development of the laser rooted in quantum physics is a testament to how our understanding of the universe at its most fundamental level can translate into tangible technologies that reshape our world. It's a perfect example of how abstract quantum concepts like energy levels and stimulated emission have practical everyday applications that impact your life profoundly. Even as we push the boundaries with quantum computing and communication, the laser remains a powerful reminder of the practical marvels unlocked by quantum mechanics. The journey through quantum physics reveals that even seemingly simple technologies are built upon incredibly complex and counterintuitive quantum principles. You've explored lasers, those ubiquitous tools which harness the power of stimulated emission to manipulate light with extraordinary precision. Now, let's turn our attention to another powerful technology deeply rooted in quantum mechanics, a technology that allows doctors to peer inside your body without ever making a cut: magnetic resonance imaging, or MRI. MRI machines. Those large cylindrical marvels of medical engineering rely on the quantum properties of atomic nuclei, particularly hydrogen atoms, which are abundant in your body. Think of these hydrogen nuclei as tiny spinning tops, each possessing a quantum property called spin. In the absence of an external magnetic field, these spins are randomly oriented like a room full of spinning tops pointing in every direction. However, when you lie inside an MRI machine, you are subjected to a powerful magnetic field far stronger than the Earth's magnetic field. This strong magnetic field forces the hydrogen nuclei to align either with or against the direction of the field, like those spinning tops aligning themselves along a north-south axis. This alignment is not perfect. Because of quantum mechanics, the nuclei also precess wobbling slightly, like a spinning top tracing a circle. The frequency of this precession, known as the Larmor frequency, is directly proportional to the strength of the magnetic field. Crucially, because the nuclei have spin, they also have a tiny magnetic moment and therefore absorb energy when they are exposed to radio waves with a frequency matching their Larmor frequency. In an MRI scan, radio frequency pulses are directed at the targeted area. When the nuclei absorb this energy, they flip to a higher energy state, aligning against the magnetic field. Then, when these excited nuclei relax back to their original aligned state, they emit radio frequency signals that are detected by the MRI machine. These signals, faint whispers from the quantum realm, form the building blocks of the MRI image. By carefully manipulating the magnetic fields and radio frequency pulses, doctors can create detailed three-dimensional images of your internal organs, tissues, and bones. MRI can detect tumors, diagnose strokes, assess joint damage, and visualize blood flow, all without any invasive procedures. Data from MRI scans provides invaluable diagnostic information, enabling doctors to create tailored treatment plans. So the next time you encounter an MRI machine, remember that it's not just a piece of medical equipment. It's a testament to the power of quantum mechanics to reveal the hidden complexities of the human body. From the alignment of atomic nuclei to the precise manipulation of radio frequency pulses. Quantum physics is the silent architect behind this life-saving technology. How will these insights into applying quantum physics in medical diagnostics influence our understanding of health and personalized medicine? You've witnessed how seemingly esoteric quantum phenomena underpin technologies like lasers and MRI machines, marvels of modern science. But what about the technology that powers the device you're likely reading this on, be it a computer, a tablet, or a smartphone? This chapter delves into the workhorses of the digital age: transistors, the tiny switches that control the flow of electricity and enable all the computations that drive our modern world, and how they rely on quantum effects. Imagine a water faucet. It has two states, open and closed, controlling the flow of water. A transistor is similar, controlling the flow of electricity in a circuit. These tiny devices, often measuring just a few nanometers across, act as switches turning the flow of electrons on or off. This on-off state represents the binary digits 0 and 1, the language of computers. By combining millions or even billions of these transistors in intricate circuits, computers can perform incredibly complex calculations. The operation of these transistors, particularly modern nanoscale transistors, is deeply rooted in quantum mechanics. At these incredibly small scales, electrons don't behave like tiny marbles moving in a predictable path. Instead, they exhibit their wave-particle duality, moving according to quantum probabilities. One key quantum phenomenon at play is quantum tunneling. Imagine trying to throw a ball over a wall. Classically, if you don't throw it hard enough, the ball simply bounces back. But in the quantum world, there's a tiny probability that the ball could tunnel through the wall, appearing on the other side, even if it doesn't have enough energy to go over. Similarly, in a transistor, electrons can tunnel through a barrier, even if they don't have enough energy to overcome it classically. This quantum tunneling effect influences the flow of electricity, determining whether the transistor is in the on or off state. Another important aspect is the discrete energy levels of electrons in the semiconductor materials that make up transistors. These energy levels are quantized, meaning electrons can only exist at specific energy values and need a very specific energy to move to a higher state. As transistors shrink to nanoscale dimensions, these quantum effects become increasingly significant, governing their performance and limitations. These quantum phenomena within transistors enable modern devices to be smaller, faster, and more energy efficient. While you might not directly perceive the quantum effects at play when using your phone, they are fundamental to its very operation. Every calculation, every image displayed, every communication sent relies on the quantum dance of electrons within those minuscule switches. As transistors continue to shrink, our ability to understand and control these quantum effects becomes even more critical. How will scientists further innovate by harnessing these ever-present quantum phenomena to create faster, smaller, and more efficient electronic devices? You've traversed the fascinating and often perplexing landscape of quantum mechanics, encountering superposition, entanglement, wave-particle duality, and the observer effect. You've seen how these concepts challenge our classical intuitions, forcing us to reconsider the very nature of reality. But the journey hasn't just been theoretical, it's been deeply practical. Throughout this exploration, one central theme has emerged with increasing clarity. Quantum mechanics isn't just an abstract theory, it's the unseen foundation upon which much of our modern technology is built. Consider the array of devices that enrich and enable our daily lives. From the lasers scanning barcodes at the checkout counter to the transistors powering the computer on your desk, quantum principles are at play. The MRI machine, allowing doctors to peer inside the human body with unprecedented detail, relies entirely on the quantum properties of atomic nuclei. The secure communication networks that protect our sensitive data depend on the unhackable nature of quantum key distribution. And on the horizon looms the quantum computing revolution, poised to solve problems previously deemed intractable and usher in a new era of scientific and technological progress. This is not an exaggeration or a simplification. The very fabric of these technologies is woven from the threads of quantum mechanics. Lasers harness the stimulated emission of photons, forcing atoms to emit light in a coordinated, coherent beam. Transistors. The building blocks of all digital devices rely on the quantum phenomenon of tunneling to control the flow of electricity. MRI machines exploit the quantum property of nuclear spin to generate detailed images of our internal organs. Each is an example of how quantum mechanics translates into tangible applications. These are not isolated examples. As we delve deeper into the quantum realm, controlling matter and energy at the atomic and subatomic level, even more revolutionary technologies are bound to emerge. Quantum sensors, with their unparalleled precision, will revolutionize everything from navigation to medical diagnostics. Quantum materials engineered with atomic-level control promise to unlock unprecedented properties for energy storage electronics and beyond. This journey through the quantum universe has demonstrated that the seemingly bizarre and counterintuitive laws of quantum mechanics are not just abstract curiosities. They are the fundamental principles that govern the world around us, enabling the technologies that shape our modern lives. Understanding quantum mechanics isn't just about pushing the boundaries of scientific knowledge. It's about unlocking the potential to solve humanity's greatest challenges and build a better future. As you reflect on this quantum revolution, what innovations do you anticipate seeing next, and how will they further blur the line between science fiction and reality? You've touched upon the revolutionary potential of quantum computing, that paradigm shift in information processing that harnesses the very fabric of quantum mechanics. But what makes these machines so different, and why are scientists and engineers so excited about their capabilities? It's time to delve deeper into the inner workings of these extraordinary devices. Recall that classical computers rely on bits, those binary switches that are either 0 or 1. A quantum computer, however, utilizes qubits, which, thanks to the principle of superposition, can exist as 0-1 or both simultaneously. This is like having a light switch that can be on-off or both at the same time, but superposition is only the first ingredient. The real magic arises from entanglement, that spooky action at a distance, where two or more qubits become linked, their fates intertwined. When qubits are entangled, measuring the state of one instantaneously influences the state of the others, regardless of the distance separating them. In a quantum computer, this entanglement allows qubits to work together in a coordinated fashion, performing calculations in parallel, exploring multiple possibilities simultaneously. Think of it like having a vast team of workers tackling a complex puzzle. A classical computer would have each worker try one solution at a time. But a quantum computer, using entangled qubits, allows every worker to try multiple solutions, simultaneously coordinating their efforts to find the right answer far more quickly. This parallelism unlocks exponential speed-ups for certain types of calculations. Problems that would take classical computers millennia to solve, such as factoring large numbers crucial for breaking modern encryption or simulating complex molecular interactions key for designing new drugs, become tractable for a quantum computer. This isn't simply a matter of being faster, it's a fundamental difference in how computations are performed, opening doors to solving problems that are currently impossible. However, building quantum computers is an immense engineering challenge. Qubits are incredibly fragile, highly susceptible to noise and disturbances from their environment. This decoherence can cause the qubits to lose their quantum properties, introducing errors into the calculations. Scientists are tirelessly working to develop error correction techniques and build more stable qubits, but these challenges remain a significant hurdle to realizing the full potential of quantum computing. Despite these challenges, progress is accelerating. Research groups around the world are exploring various qubit technologies, from superconducting circuits to trapped ions to topological qubits, each with its own strengths and weaknesses. Data from leading institutions consistently demonstrates increasing qubit counts and improved coherence times. The journey to build truly scalable and fault-tolerant quantum computers is a long and arduous one. But the potential rewards are so transformative that it is fueling intense global competition. As these machines mature, they will revolutionize fields from medicine and materials science to artificial intelligence and cryptography, ushering in a new era of scientific discovery and technological innovation. How will this unprecedented computational power reshape our understanding of the universe, and what new ethical considerations will arise as we unlock these immense capabilities? You've touched upon the power of quantum computing, recognizing that it leverages quantum phenomena like superposition and entanglement to unlock computational capabilities far beyond those of classical computers. However, to truly understand this quantum revolution, you must first understand the qubit, the fundamental unit of quantum information. What exactly is a qubit, and how does it differ from the classical bit that powers your everyday devices? While a classical bit is like a switch that is either on or off, representing a 0 or a 1, a qubit exists in a far more nuanced state, due to the quantum principle of superposition. Unlike a light switch that can only be up or down, think of a dimmer switch. A qubit can exist in a state that is a blend, a combination, or a superposition of both 0 and 1 simultaneously. This means a single qubit can represent much more than just two states. It can represent any point on a continuum between 0 and 1. Mathematically, this is often represented as a sphere where the north pole is, the south pole is 1, and every other point on the sphere is a unique superposition of those two states. Moreover, qubits can be linked together through quantum entanglement, that spooky action at a distance, where two or more qubits become intrinsically connected, their fates intertwined. When qubits are entangled, measuring the state of one instantaneously influences the state of the other, regardless of the distance separating them. This entanglement allows qubits to work together in a coordinated fashion, performing calculations in parallel and exploring multiple possibilities simultaneously. A set of 3 entangled qubits, for instance, can exist in 8 different possible states at the same time compared to the 3 states it has without entanglement. The power of a quantum computer scales exponentially with the number of qubits. This means that adding even a single qubit dramatically increases the computer's processing power. This is why scientists are so intensely focused on building quantum computers with ever-increasing numbers of stable and reliable qubits. It's important to note that unlike classical bits which maintain their values unless actively changed, qubits are extremely fragile, susceptible to environmental noise that can disrupt their delicate quantum states, leading to errors in calculations. This is known as decoherence, and it represents a major hurdle in the development of practical quantum computers. The challenge, therefore, lies not just in creating qubits, but in creating qubits that are stable, controllable, and scalable, all while preserving their delicate quantum properties. These nanoscale systems can be realized using a range of physical systems, from superconducting circuits to trapped ions, each with distinct strengths and weaknesses. Understanding these differences is key to unraveling quantum mechanics. How will these advancements in qubit technology influence the very nature of information itself? You now understand that qubits, unlike classical bits, can exist in a superposition of states representing a spectrum of possibilities simultaneously, and can be linked through entanglement, allowing them to act in concert. But what does this translate to in terms of actual computational power? Just how much faster? How much more powerful can a quantum computer truly be? Consider this: a classical computer tackles a problem by trying one solution at a time, methodically working its way through a list of possibilities. This approach is often slow, especially when dealing with extremely complex problems that have a vast number of potential solutions. A quantum computer, however, leverages superposition to explore many potential solutions simultaneously. Because a quantum particle is existing in all possible states, you are testing every possible solution at once. It's as though a classical computer has to navigate a maze one path at a time, while a quantum computer can explore every path in the maze all at once. This difference leads to what's called quantum supremacy, the point at which a quantum computer can perform a calculation that is practically impossible for even the most powerful classical supercomputer. Some algorithms, such as Shor's algorithm for factoring large numbers, show exponential speedups on a quantum computer compared to the best-known classical algorithms. This means that as the size of the problem increases, the time it takes a quantum computer to solve, it grows much more slowly than it does for a classical computer. The implications of this computational speed are staggering. Imagine simulating complex molecular interactions to design new drugs and materials with atomic-level precision, a task currently beyond the reach of even the most powerful supercomputers. Envision breaking modern encryption algorithms currently used to secure everything from online banking to government communications, rendering them vulnerable to attack. But it's not just about speed. It's about enabling entirely new kinds of computations. Quantum computers are particularly well suited for optimization problems, such as finding the most efficient routes for delivery trucks, or optimizing investment portfolios tasks that involve navigating a vast landscape of possibilities. They also hold immense promise for machine learning, enabling the development of more powerful AI algorithms that can learn from data and make predictions with unprecedented accuracy. It is also important to remember that there are still a number of engineering hurdles. Creating a truly stable and scalable quantum computer requires controlling the delicate quantum states of qubits with extreme precision. However, there are numerous constantly being innovated ways to push the limitations of the quantum state. The power of qubits harnessed through superposition and entanglement promises to unlock a new era of computational possibilities, revolutionizing fields from medicine and materials science to artificial intelligence and cryptography. As we unlock the immense power of quantum computing, how will humanity harness its potential to solve its greatest challenges and build a better future? You've explored the immense computational potential that quantum computers promise to unlock, revolutionizing fields like cryptography, artificial intelligence, and materials science. But imagine a world where these quantum machines are not just crunching numbers, but actively saving lives. This is the promise of quantum medicine, a field where quantum computing and other quantum technologies are poised to transform healthcare from drug discovery to personalized treatment. One of the most promising applications lies in the design and discovery of new drugs. Developing new pharmaceuticals is a notoriously lengthy and expensive process, often taking years and costing billions of dollars. This is in part because it is so difficult to accurately simulate how drugs will interact with molecules in the human body. Current computational methods struggle to model the intricate quantum interactions between drug molecules and complex biological systems. A molecule is nothing but a collection of atoms linked by quantum forces. Quantum computers, however, with their ability to perform exponentially complex calculations, are ideally suited for simulating these quantum interactions with unprecedented accuracy. Imagine designing a drug molecule atom by atom, predicting precisely how it will bind to a target protein, and optimizing its properties for maximum effectiveness and minimal side effects. You have absolute precision at your fingertips. This capability extends beyond drug discovery to personalized medicine, tailoring treatment plans to an individual's unique genetic makeup. Each person's genome contains subtle variations that can influence how they respond to different medications. Predicting these individual responses requires simulating complex biological systems, a task that is currently beyond the reach of classical computers. Quantum computers, with their ability to model complex molecular interactions, could analyze an individual's genetic data and predict their response to different treatments with far greater accuracy. This could lead to personalized drug regimens optimized for each patient's unique needs, minimizing side effects and maximizing the chances of success. This approach could reduce healthcare costs. But the transformative potential doesn't stop at drug design. Quantum sensors, with their ability to measure physical quantities with unparalleled precision, could revolutionize medical diagnostics. Imagine sensors capable of detecting diseases at their earliest stages long before conventional methods can detect them. Data from research projects, some including these quantum sensors, is promising. As the field of quantum medicine continues to develop, and as quantum computers become more powerful and accessible, we can expect to see a wave of innovation that transforms healthcare as we know it. From designing personalized drugs to detecting diseases earlier and more accurately, quantum mechanics promises to usher in a new era of precision and effectiveness in medicine, greatly improving human lives. As quantum medicine continues to advance, what new ethical considerations will arise regarding data privacy, access to these advanced technologies, and the potential for enhancing human capabilities? You've witnessed how quantum computing promises to revolutionize medicine, materials, science, and artificial intelligence, enabling solutions to previously intractable problems. Yet there's a looming shadow, a potential threat that emerges from this very power. Quantum computers could also break much of the encryption that protects our digital world. This realization has spurred intense interest in a new field that leverages quantum mechanics not to break codes, but to create cryptographic systems, so secure they are in principle unbreakable. Quantum cryptography. Classical cryptography relies on mathematical algorithms that are, in theory, difficult to crack, but as computers become ever more powerful, these algorithms become increasingly vulnerable. Quantum computers, in particular, pose a grave threat to many existing encryption methods, especially those used to secure online banking and government communications. It's like an arms race where code makers are struggling to stay one step ahead of code breakers. Quantum cryptography, however, offers a fundamentally different approach to security. Instead of relying on mathematical complexity, it leverages the laws of quantum physics, specifically the principles of superposition and the observer effect, to create cryptographic systems that are provably secure against any eavesdropping attempt, regardless of the eavesdropper's computational power. This provides perfect security. The algorithm itself is safe from being attacked. The most well-known example of quantum cryptography is quantum key distribution, or QKD, discussed earlier. It uses the quantum states of single photons of light to transmit a secret encryption key between two parties. The beauty of QKD is that any attempt to intercept these photons and measure their quantum states will inevitably disturb the system, introducing detectable errors into the key. These are quantum states, after all, which rely on observation for verification. The power of QKD lies in its ability to guarantee security not based on the difficulty of a mathematical problem, but on the fundamental laws of physics. Eavesdropping is detectable. Data from experiments confirm how robust this quantum-powered key exchange is, even over long distances or under highly noisy conditions. This doesn't mean quantum cryptography is impervious to all attacks. While the key exchange itself is secure, the devices used to generate and detect the photons can still be vulnerable to side-channel attacks. Moreover, QKD only addresses the key exchange problem. The subsequent encryption and decryption of the actual message still relies on classical algorithms. Despite these challenges, quantum cryptography represents a significant step forward in the quest for unbreakable security. It offers a future where our sensitive data is protected not by complex algorithms that may one day be cracked, but by the immutable laws of the quantum realm. With the emergence of quantum-resistant algorithms, what role will quantum cryptography play in securing our increasingly interconnected world? You've explored the transformative potential of quantum computing across diverse fields, from medicine and cryptography to materials, science, and artificial intelligence. But consider another pressing challenge facing humanity: the need for cleaner, more efficient, and more sustainable energy solutions. It is a crucial thing to solve given today's world. Quantum computing holds tremendous promise for revolutionizing energy management and optimizing power grids. Modern power grids are incredibly complex systems involving countless generators, transmission lines, and consumers. Managing the flow of electricity, efficiently balancing supply and demand, and preventing blackouts requires solving incredibly complex optimization problems, with many quantum researchers currently working to solve these issues. These challenges become even more daunting with the increasing integration of renewable energy sources like solar and wind, which are inherently intermittent and unpredictable. This can result in unstable grids. Classical computers struggle to handle the sheer scale and complexity of these optimization problems. Quantum computers, however, with their ability to explore vast landscapes of possibilities, simultaneously offer a powerful new approach to optimizing power grid operations. One area where quantum computing can make a significant impact is in improving grid stability. Predicting demand is hard. Predicting when and where a storm will hit is hard as well. However, quantum computers can compute millions of simulations in quick succession, which can then be averaged into more reliable models. Another crucial application lies in optimizing energy storage. Modern power grids increasingly rely on battery storage systems to smooth out fluctuations in supply and demand and to integrate renewable energy sources more effectively. Quantum computers could optimize the charging and discharging of these batteries, maximizing their efficiency and extending their lifespan. Moreover, quantum machine learning algorithms could be used to improve energy forecasting, predicting demand and supply with greater accuracy. This would allow grid operators to anticipate fluctuations and adjust resources accordingly, reducing waste and improving overall efficiency. So it is not simply a means to store more efficiently, but consume more intelligently. The journey to deploy quantum computing in energy management is only just beginning, but the potential benefits are immense. A quantum-optimized energy grid would be more efficient, more resilient, and more sustainable, reducing our reliance on fossil fuels and paving the way for a cleaner energy future. This is why so many private and government organizations are dedicating money to research. As quantum algorithms for energy optimization become more sophisticated and quantum computers become more powerful, how will this revolutionary technology transform the energy landscape and help us build a more sustainable future? You've seen how quantum computers offer transformative potential in areas from cryptography to medicine to energy. A central aspect of this promise lies in their unparalleled ability to simulate complex molecular interactions, providing insights that are simply inaccessible to classical computers. So what makes simulating molecules so difficult, and why are quantum computers uniquely suited to tackle this challenge? Molecules at their most fundamental level are collections of atoms bound together by quantum forces. Understanding the behavior of molecules, how they interact with each other, how they react, and what properties they possess, requires accurately modeling these quantum interactions. This, in turn, requires solving the Schrodinger equation, a cornerstone of quantum mechanics that describes the behavior of quantum systems. A lot of modern science relies on this fact to perform experiments. The problem is that the Schrodinger equation is incredibly complex, and for molecules with more than a few atoms, it becomes virtually impossible to solve exactly using classical computers. The computational cost scales exponentially, with the number of atoms quickly exceeding the capabilities of even the most powerful supercomputers. It is for this reason that it requires great amounts of energy to perform this task. The fundamental difficulty arises from the fact that electrons in molecules exist in a superposition of states, interacting with each other in a tangled web of possibilities. Accurately capturing this superposition requires representing a vast amount of information, far more than a classical computer can efficiently handle. Even a relatively small molecule can have an astronomically large number of possible quantum states, which means the amount of processing grows non-linearly. Quantum computers, however, are perfectly suited for simulating quantum systems. Qubits, with their ability to exist in a superposition of states, can directly represent the quantum states of electrons in a molecule. Entangled qubits can accurately model the complex interactions between electrons, capturing the correlations that are crucial for determining a molecule's behavior. It's a perfect match, a quantum system simulating another quantum system. A tool mimicking its goal perfectly. This ability to accurately simulate molecules holds immense potential for a wide range of applications. It could revolutionize drug discovery, allowing scientists to design new drugs with unprecedented precision, tailoring their properties to specifically target disease-causing molecules. In materials science, it could enable the design of new materials with extraordinary properties, such as superconductors, that operate at room temperature or lightweight, ultra-strong composites. In chemistry, it could unlock a deeper understanding of chemical reactions leading to more efficient industrial processes and new ways to synthesize complex molecules. It also promises advances in our understanding of the behavior of chemicals. As quantum algorithms for molecular simulation become more sophisticated and quantum computers become more powerful, what scientific breakthroughs will be unlocked, and how will they transform our understanding of the world around us? You've journeyed deep into the heart of quantum mechanics, exploring concepts that challenge our everyday intuitions, and witnessing how they are already shaping our world in profound ways. As you reach the culmination of this journey, it's time to reflect on the full scope of the quantum revolution and envision the transformative potential of these technologies across every facet of human existence. From revolutionizing medicine to safeguarding our digital information and optimizing energy grids, quantum mechanics stands poised to address some of humanity's most pressing challenges. Quantum computers are not just faster calculators. They are tools that can unlock new insights into the fundamental laws of nature, enabling the design of new drugs, new materials, and new energy sources with unprecedented precision. The old world of computers can now be replaced with new technologies. Quantum cryptography promises a future where our communications are secure against any eavesdropping attempt, safeguarding our privacy in an increasingly interconnected world. Data can now be secured without fear of being attacked. Quantum sensors, with their ability to measure physical quantities with unparalleled sensitivity, will enable new discoveries in fields from medicine to geology, allowing us to probe the universe in ways never before imagined. They give new eyes to blind. These are not merely incremental improvements. They represent fundamental shifts in how we approach problem-solving information processing and our understanding of the universe. The quantum future will require a shift in people's minds. There must now be a great step forward in quantum knowledge. We as a civilization are also held back without access to higher-performing machines. Quantum technology isn't about replacing what we already have, but it's more about expanding our horizons, enabling new possibilities, and solving problems that are currently beyond our reach. It is a new set of capabilities. It's a new tool belt. That is something that we have to embrace or otherwise risk being left behind. Of course, this quantum revolution will not be without its challenges. We must carefully consider the ethical implications of these powerful technologies, ensuring they are used for the benefit of all humanity and not just a select few. Quantum cryptography may need to be considered with respect to protecting military secrets, as well as in regard to our fundamental right to privacy as a people. Despite those challenges, this represents a journey, an ascent into quantum mechanics. The exploration has been a good thing. It is something we need to further understand in order to push the boundaries of human knowledge. It's been the wildest rulebook we have ever seen in the universe. As you look towards this quantum future, what responsibility do you think scientists, policymakers, and citizens have in shaping the development and deployment of these transformative technologies? You've reached the end of this exploration into the quantum realm, a journey that has taken you from the seemingly simple act of flipping a light switch to the intricate workings of quantum computers and the very fabric of reality. It's been a trip that began by asking the core questions of how the world around us even works. Now the journey itself is coming to a close, and it is time to look back. As you reflect on this quantum quest, several key insights emerge. First, the universe at its most fundamental level operates under rules that are often profoundly counterintuitive. Superposition, entanglement, wave-particle duality. These are not just abstract concepts. They are real phenomena that challenge our classical intuitions and force us to reconsider our understanding of how the world works. This is not the end of quantum mechanics, but the end of the first step towards fully exploring what it has to offer. Second, quantum mechanics is not just a theoretical curiosity. It is the foundation of much of modern technology. From the lasers that scan barcodes to the transistors powering our computers, quantum principles are at play, often unseen, but always essential. You've also seen that even Albert Einstein was not immune to how hard it is to understand it at times. But despite being unable to reconcile his theories with these bizarre quantum elements, his challenge was still a force for growth. Third, the quantum revolution is far from over. It is only just beginning. Quantum computing, quantum cryptography, quantum sensing, and quantum materials are poised to transform industries and redefine what is possible, offering solutions to some of humanity's most pressing challenges. This isn't just about faster computers or more secure communications. It's about a new way of thinking about information computation and the nature of reality itself. The quantum world isn't simple and linear. Instead, it is messy. It is probabilistic. The possibilities range from likely to virtually impossible, but not impossible. Now the universe can become accessible in a whole new way. Throughout this journey, you've encountered paradoxes and mysteries that challenge our classical intuitions and force us to confront the limitations of our understanding. We have seen that this new frontier offers as many questions as it answers. As a science, there is a reason to be hopeful that we will be able to conquer the challenges thrown our way. The quantum realm is not just a collection of strange phenomena. It's a gateway to a deeper understanding of the universe and our place within it. And it is more important now than ever, given today's reliance on technology. Embrace the unknown, question your assumptions, and never cease to explore the weirdest rulebook ever written, the laws of quantum physics. It is not a simple path, but it is worthwhile. Now, as you step back into the classical world, what aspect of the quantum realm will linger most vividly in your mind, and how will it shape your perspective on the world around you? You now stand at a vantage point, having traversed the landscape of quantum mechanics, exploring its counterintuitive concepts, and witnessing its transformative potential. You have now stepped into what comes next in this area of exploration. Now take a moment to consolidate the insights gained and fully appreciate the implications of the quantum world. Perhaps the most profound takeaway is the realization that at the heart of reality lies probability and uncertainty. Unlike the classical world where objects have definite properties and predictable behaviors, the quantum realm is governed by probabilities. A quantum particle before measurement exists in a superposition of multiple states, a blurry mix of possibilities. The very act of observation, as demonstrated in the double slit experiment, forces the particle to choose a single state, collapsing the wave function and bringing definiteness into existence. This inherent uncertainty isn't just a matter of our inability to precisely measure quantum properties. It's a fundamental characteristic of reality at the quantum level. The position, momentum, and other properties of a particle are not predetermined, but rather described by a probability distribution. This means that we can only predict the likelihood of finding a particle in a certain state, not its exact state, with certainty. We only see snapshots. This probabilistic nature of the quantum world has far-reaching consequences. It challenges our classical notions of causality, suggesting that events are not always uniquely determined by their past. The future is not fixed, but rather a tapestry of possibilities shaped by chance and our interactions with the quantum realm. There are many new things that are coming about due to this very nature. Despite this inherent uncertainty, quantum mechanics is not random or chaotic. It is governed by precise mathematical laws, and its predictions, while probabilistic, have been confirmed by countless experiments to an extraordinary degree of accuracy. It is a blend of chance and determinism, where probabilities are precisely defined and the evolution of quantum systems is governed by elegant equations. It has come to a point where, when looking at the data, there is no other conclusion that can be drawn. Embracing this probabilistic worldview requires a shift in perspective, a willingness to accept uncertainty as a fundamental aspect of reality. It means acknowledging the limits of our knowledge and embracing the inherent mystery of the quantum realm. The understanding of the probability of these events has also expanded into modern machine learning and allows us to perform even more refined models. The more that we explore, the more we grow. However, our efforts to fully unlock this level of possibility does not come without challenges and danger. As a member of the audience, remember to stay aware of what can occur when these tools are given to the wrong hands. Having explored the depths of superposition and wrestled with the implications of the observer effect, how will you now embrace this inherent uncertainty in your own life, acknowledging the multitude of possibilities that exist in every moment? You've journeyed through the quantum world, witnessing firsthand the counterintuitive nature of superposition entanglement and the probabilistic behavior of particles. However, one concept continually reemerges, weaving its way through nearly every aspect of quantum mechanics: the crucial role of observation. The very act of measurement, it turns out, is not a passive recording of pre-existing properties, but an active participant in shaping quantum reality. You can almost see what happens as if you are peering from just outside the universe itself. Think back to the double slit experiment. When electrons passed through the slits without being observed, they created an interference pattern behaving like waves spreading out in a probabilistic manner. This is a quantum particle existing at a single place at no single time. But the moment scientists attempted to measure which slit each electron passed through, the interference pattern vanished, and the electrons behaved like particles, creating two distinct bands. The observer in this case was not a person, but a machine. However, this made a profound difference. This very change to what is being studied is what this chapter is about. This observer effect isn't just about conscious observation. What does the machine have to do with it? Any interaction that forces a quantum system to choose a single state from a superposition of possibilities, any measurement, any interaction with the environment collapses the wave function and brings definiteness into existence. Think of it a different way. What if we took the machine out of the equation? If we could somehow measure the machine without the machine being able to observe the electrons, the interference pattern would exist once more. The observer effect highlights the interconnectedness between the observer and the observed, blurring the line between the subject and object. In the quantum realm, the observer is not a separate entity, impartially recording the properties of a pre-existing reality. Rather, the observer is an active participant shaping the reality they observe. It could even be argued that a form of consciousness can come about in this system through the measurements themselves. This has profound implications for our understanding of objectivity. In the classical world, we assume an objective reality exists independently of our observations. A tree falls in the forest, and it makes a sound whether or not anyone is there to hear it. Quantum mechanics, however, challenges this assumption, suggesting that reality is not always independent of our interactions with it. This leads to questions about the nature of objective existence. It may seem to go against the heart of science, but this is something that must be considered in the years to come. The act of observation, it turns out, is not merely a passive recording of pre-existing properties. It's an active participant in shaping quantum reality, a dance between observer and observed that lies at the heart of the quantum world. As you reflect on the significance of observation in shaping quantum reality, consider how this challenges our assumptions about objectivity and the role of the observer in the world around you. You've explored the core tenets of quantum mechanics, witnessed its impact on modern technology, and wrestled with its philosophical implications. Perhaps no concept encapsulates the strangeness and interconnectedness of the quantum realm more profoundly than entanglement. As you now reflect upon it, what does it tell us about the universe itself? Think back to what entanglement means. Two or more particles become linked in such a way that they share the same fate regardless of the distance separating them. Measure a property of one particle, and you instantly know the corresponding property of the other, even if they are light years apart. This is not the transfer of information faster than light. Instead, it is the manifestation of a shared reality, a unified quantum system. Now imagine the vastness of the cosmos, stretching billions of light years in every direction. Imagine the countless stars, galaxies, and nebulae, all swirling and interacting, shaped by gravity and electromagnetism. What if at the most fundamental level, this entire cosmic tapestry is also interwoven with threads of quantum entanglement? This is not mere speculation. Scientists theorize that entanglement may have played a crucial role in the very early universe during the period of rapid expansion known as inflation. During this era, the entire universe was compressed into an incredibly small volume where quantum effects would have been dominant. It's possible that many, if not all of the particles in the universe were once entangled, their fates linked from the very beginning. The early universe was a quantum playground. Even today, entanglement may play a role in the structure and evolution of the cosmos. Some scientists theorize that entanglement may be involved in the formation of black holes or in the behavior of dark matter, those mysterious substances that make up the majority of the universe's mass. It may even be that it informs the processes of life itself. Though scientists are unsure, it is possible that life is formed and made more efficient through quantum mechanics. While these ideas are still highly speculative, they highlight the profound implications of quantum mechanics for our understanding of the cosmos. If entanglement does indeed permeate the universe at the largest scales, it suggests a level of interconnectedness that defies our classical intuitions. If proven correct, it would force us to completely reconsider what we know about physics. This shows what a new age of discovery can do. The journey into quantum mechanics has revealed that the universe is far stranger, more interconnected, and more mysterious than we ever imagined. As you contemplate the possibility of a fundamentally entangled cosmos, what does this suggest about the nature of reality and our place within it? You've explored the quantum world, grappling with its strangeness and marveling at its potential. You have seen how these laws of the cosmos have come to have an effect on what may be humanity's greatest invention. The journey now ends, at least for this volume, with looking at the core themes of what this all means to our greater study of science. Now it is time to fully recognize the profound truth that quantum mechanics is not just another branch of physics. It is the universal language that underlies all of reality. From the smallest atoms to the largest stars, from the intricate workings of biological molecules to the vast expanse of the cosmos, quantum mechanics reigns supreme. It's the same set of rules which allow electrons to have a superposition that can then provide the basis for technologies for the future. As you now remember, it wasn't enough to have superposition, but entanglement is also required. The laws of chemistry are ultimately governed by quantum mechanics, dictating how atoms interact and form molecules. The behavior of materials, from the strength of steel to the conductivity of semiconductors, arises from the quantum properties of electrons. And the fundamental forces that shape the universe, electromagnetism, the weak force, and the strong force, are all described by quantum field theories. It could even be hypothesized that if all the sciences were to go, quantum mechanics may be the last one standing. This universality extends beyond the physical world. The principles of quantum mechanics are now being applied to fields like information theory and computer science, leading to revolutionary technologies like quantum computing and quantum cryptography. Even in biology, scientists are beginning to explore the role of quantum effects in processes like photosynthesis and enzyme catalysis. To be able to understand these quantum effect-driven processes gives a new glimpse into what happens when life is made. It's also important to remember what this all means. Many have taken to believing in pseudoscience by using ideas like quantum healing and attempting to imbue a crystal with a certain energy for a purpose. All things must be viewed with a critical lens. Quantum is not magic. It may seem like it now, but we must remember that it is just another area of science waiting to be uncovered. So, although science fiction does take many ideas from this realm, it is not always a science fact. So it is better to remain skeptical. This journey into quantum mechanics has been an exploration of the fundamental laws that govern our universe, a testament to the power of human curiosity and the relentless pursuit of knowledge. It's a reminder that the universe is far stranger and more wonderful than we could ever have imagined. These ideas and topics must be at the forefront of the human mind, or we face being left behind. Having explored how quantum mechanics is the universal language of physics, consider the importance of further exploration. What new and unpredictable advancements can we hope to find? You now stand at the end of this journey. The final word rests with you, and given what has occurred, it is time to truly embrace it. In this final chapter, that which made this all so difficult is going to be discussed. We have looked at the different areas where it shows through and seen the great power it gives us. So how do we make this all easier? Throughout this exploration of the quantum realm, you have encountered concepts that challenge our everyday intuitions, ideas that seem to defy logic and common sense. Superposition, entanglement, wave-particle duality, the observer effect. These are not concepts that come naturally to our classical minds. They require a willingness to abandon preconceived notions and embrace the seemingly impossible. It is not to say they are all useful, but if these concepts are possible, what does that mean for what else may be out there? Perhaps this is what Einstein was referring to when he mentioned the spooky action. There are things in this world that are going to conflict with what is already known. But, as you may have learned, it is this sort of challenge that has made quantum mechanics as great as it is today. But it is also what helps us understand where reality might be heading. The core principles in quantum physics have paved the way for what are now revolutionary fields. So while it is not quite magic, there may be a whole new area that is awaiting us as quantum physics continues to be explored. Embracing the counterintuitive nature of quantum physics is not about rejecting logic or reason. It is about expanding our understanding of what is possible. It is about recognizing that the universe operates under rules that are far more subtle and complex than we initially imagined. This is how humans have grown over thousands of years. There will be much to learn from these technologies for years to come. And there will surely be even more advancements for years to come. and who knows what lies in the next chapter. In that regard, how has your exploration of quantum mechanics reshaped your view of what is possible both in the realm of science and in the broader world around you? You now stand at the end of our journey, one that you have hopefully found to be as informative as it is eye-opening. It is a time to reflect on all that you've seen, and in this last discussion, to have it all make sense, to put the pieces of the puzzle together, so to speak. Through this exploration of quantum mechanics, you've encountered mind-bending concepts, explored cutting-edge technologies, and pondered profound philosophical implications. Perhaps at times, it has felt like a journey into a world far removed from your everyday reality. However, this is not the case, and that will be the final point for which we need to discuss. What then, if all these things have been far too outlandish? Now in this final word, it should now be understood that quantum mechanics is not just the realm of physicists in white coats or the secret ingredient in high-tech gadgets. It's an intrinsic part of your everyday reality, shaping the world around you in ways you may never have imagined. Consider the colors you see. The vibrant hues of a sunset, the lush green of a forest, the deep blue of the ocean. All these colors arise from the quantum interactions between light and matter. When light strikes an object, electrons in the object's atoms absorb and emit photons of specific energies determined by the quantum energy levels of the atoms. This is all due to quantum mechanics, a force that brings light and life to what we see. Think about the materials you touch. The strength of steel, the flexibility of plastic, the conductivity of copper. These properties all arise from the quantum behavior of electrons within the material. The very solidity of matter. The fact that you can stand on the floor without falling through is a consequence of quantum mechanics. If classical physics were accurate, you wouldn't be able to touch anything at all. Consider your own body. From the intricate workings of DNA to the complex processes of cellular respiration, quantum mechanics plays a vital role. The enzymes that catalyze biochemical reactions rely on quantum effects to accelerate those reactions, enabling life to function. The process of photosynthesis, which provides the oxygen you breathe, is initiated by the absorption of photons by chlorophyll molecules, a fundamentally quantum process. It may sound outlandish, but remember how we stated earlier that scientists are exploring life through a quantum lens. There may be more about it in the future. So whether you are consciously aware of it or not, quantum mechanics is constantly at work shaping your everyday reality. From the colors you see, to the materials you touch, to the very processes that keep you alive, quantum mechanics is the unseen foundation upon which our classical world is built. But it's the potential that really excites scientists of today, and also you now at the end of your journey. These are just the beginning. That means it is a blank slate for those who now know to fill in. There is an entire world of technology waiting to be created and understood thanks to what you know now about quantum mechanics. As you move forward, how will you recognize and appreciate the quantum world at play in your everyday experiences, finding wonder in the seemingly mundane? You have now reached the culmination of your exploration into the quantum world. It has been a journey of discovery, a voyage into the strange and often counterintuitive realm that governs the universe at its most fundamental level. Now, having examined the core tenets of quantum physics, witnessed its impact on technology, and pondered its philosophical implications, it is time to stand back and truly appreciate the grand scope of it all. From the smallest subatomic particles to the largest cosmic structures, quantum mechanics provides the fundamental framework upon which all of reality is built. You've seen this in the double slit experiment, which shows how even something like an electron can act like both a wave and a particle. You've seen how observation can affect the results of an experiment, and how two entangled particles can interact with each other despite any distance. You also saw that the quantum field is a source of powerful technologies. This is just the barest of the iceberg. Because of the study of quantum mechanics, you can now know that the colors of the sunset, the solidity of a table, and the very workings of your own body are all a consequence of the rules of quantum mechanics. The laws governing the behavior of atoms, the forces that hold matter together, and the processes that make life possible. All these are governed by the principles of quantum mechanics. It is the language of physics. All of the physics that came before all the work that has been done is but a precursor to what we have today. This is not merely a theoretical framework. It is a powerful tool that is transforming our world. Quantum computing promises to revolutionize medicine materials, science, and artificial intelligence. Quantum cryptography offers the potential for unbreakable security. Quantum sensing is poised to unlock new discoveries in fields ranging from astronomy to medicine. Quantum materials have now opened up all sorts of new doors for creation, many of them still unknown to us. But perhaps the greatest lesson of this journey is the importance of embracing the counterintuitive. The quantum world challenges our classical intuitions, forcing us to question our assumptions and to accept uncertainty as a fundamental aspect of reality. If that is accepted, then so much more is possible. Remember that no matter what happens, always keep exploring the unknown. As you keep up your curiosity, you will be rewarded. The quantum future is not just about technological advancements. It is about a fundamental shift in our understanding of the universe and our place within it. Now, as you conclude your exploration, what questions remain unanswered, and how will you continue to explore the wonders of the quantum realm? You've completed your journey through the quantum world, a voyage that has taken you from the familiar to the fantastically strange. You have seen what is in our world and what may come. It is all thanks to quantum mechanics. The story has now come to the end. But as you now know, this journey of discovery doesn't end with the last page of this guide. The quantum realm is not a closed book. It is an open door inviting you to continue exploring, questioning, and embracing the wonders of the unknown. You have heard about the ways that quantum mechanics has made modern technologies. You are now ready to embrace the challenges that it puts forth. The quantum world, with its superposition, entanglement, and observer effect, may seem beautifully paradoxical. It challenges our classical intuitions, forcing us to rethink what we believe about reality. But it is in this very paradox that the beauty and power of quantum mechanics truly lie. To understand this field, you must embrace it. Let go of the need for everything to make sense, and instead embrace the mystery. Accept that a particle can exist in multiple states at once, that the act of observation can shape reality, and that two particles can be linked in a way that defies distance. It is okay if things don't make sense, as there may be another truth that we cannot understand. It is also important to remember what Einstein said: if you can't explain it simply, you don't understand it well enough. The key to appreciating quantum mechanics isn't about finding all the answers. It's about asking the right questions. It's about remaining curious, about seeking out new information, and about never losing your sense of wonder. It's about staying curious and embracing new technologies that may come. As you go forth, continue to explore. Pick up the A Simple Guide and read through it again. Read about the double slit experiment and also about Schrödinger's cat. See that every day this world can be explained. Remember that the quantum world is all around you. It is the very foundation of our universe, and the source of many of the technologies that shape your life. You've now joined the ranks of those who can see beyond the everyday, of those who understand that the universe is far more strange and more wonderfully weird than we ever imagined. So keep your mind open. Keep questioning. Keep exploring. And remember that the journey of discovery never truly ends. What will your next steps be? You have now reached the end of this exploration into the quantum realm, a journey that has taken you from the familiar world around you to the bizarre and beautiful landscape of the subatomic. You have explored some of the basics, seeing how these ideas are what shape our world. It is more than this. The study of quantum physics gives us a new means to study the universe. But the journey continues. As you have come to understand, the seemingly paradoxical nature of quantum mechanics is not a weakness, but a strength, a window into a deeper reality. The concepts you've explored, superposition, entanglement, the observer effect, and wave-particle duality may challenge your classical intuitions, but they also offer a richer, more complete understanding of the universe and its secrets. The study of quantum mechanics is a key to understanding the world around us. It is a source of incredible technologies. Because of this, quantum mechanics is a lens through which we can view not only the smallest particles, but also the largest cosmic structures. What if quantum entanglement played a role in the very fabric of space-time connecting galaxies across vast distances? What if quantum effects were crucial in the formation of black holes or the behavior of dark matter, the invisible substance that makes up the majority of the universe's mass? With the study of quantum mechanics, all of this is possible. The possibilities seem to never end, from the intricate dance of atoms to the grand sweep of the cosmos, quantum mechanics offers a new perspective on the mysteries that have captivated scientists and thinkers for centuries. It is a means to measure the world as we have never seen it before. The technologies that are built upon quantum mechanics, quantum computers, quantum sensors, and quantum communication systems promise to revolutionize everything from medicine and materials, science, to artificial intelligence and cryptography. These are tools that allow us to push the limits of the possible. Quantum also allows for an expansion of human understanding and innovation. The journey through the quantum world has been a testament to human curiosity, ingenuity, and the relentless pursuit of knowledge. It's a reminder that the universe is far stranger, more interconnected, and more wonderfully weird than we could have ever imagined. It is, after all, the weirdest rulebook that we have ever seen. So the final journey ends with what remains to be discovered as you continue to explore the wonders of the quantum realm. What new mysteries will you seek to uncover? And how will you contribute to the unfolding story of the universe? You've journeyed far, delving into the intricacies of quantum mechanics, from the fundamental principles that govern the subatomic world to the revolutionary technologies emerging from this profound understanding. This exploration has not been merely an intellectual exercise. It's been a transformative experience, reshaping your perception of reality and revealing the hidden depths of the universe. As we conclude this adventure, let us take a moment to reflect upon the path traveled and the profound insights gained. Recall those early chapters where we attempted to make sense of the seemingly contradictory nature of the quantum world. We found that the world of quantum physics is far removed from our everyday macroscopic experiences. The counterintuitive nature of superposition, that a particle can exist in multiple states simultaneously until measured confronted our ingrained classical understanding of determinism and causality. We then learned how the very act of observation, or any interaction, collapses this superposition into a single definite state, demonstrating the profound observer effect a phenomenon that even Einstein struggled to reconcile with his classical worldview. This was not simply an anomaly, however. As the field of quantum mechanics continues to develop, it is clear that the observer effect has had a profound impact on the development of modern science and technology. The double slit experiment, a seemingly simple setup, yielded results so paradoxical they challenged the very foundations of physics. The inherent uncertainty at the heart of quantum mechanics, where we can only speak of probabilities rather than certainties, forced a re-evaluation of our classical notions of predictability. And then there's entanglement, that spooky action at a distance, where particles remain mysteriously linked, their fates intertwined even across vast distances. Einstein's skepticism, though understandable from a classical perspective, was ultimately overcome by irrefutable experimental evidence demonstrating the power and strangeness of the quantum world. The implications of this are truly profound. But this journey into the quantum realm has not been confined to theoretical discussions. You've witnessed how quantum mechanics forms the bedrock of countless modern technologies. From the lasers that read barcodes to the transistors that power your devices, from the MRI machines that provide detailed medical images to the unhackable communication networks promised by quantum key distribution, quantum mechanics is not merely a theoretical framework, but a practical tool shaping our world. And this is only the beginning. We've explored the potential of quantum computers capable of solving problems that are currently intractable for even the most powerful classical machines, revolutionizing fields from medicine and materials science to artificial intelligence and climate change modeling. We've seen how quantum mechanics can lead to quantum materials with hitherto unseen properties, and how quantum sensing offers unprecedented precision in measurement. The technological applications are vast and continuously expanding. This exploration has also touched upon the philosophical implications of quantum mechanics, challenging our ingrained notions of objectivity and causality. Schrödinger's cat, a thought experiment designed to illustrate the absurdity of applying quantum principles to macroscopic systems, also serves as a powerful reminder of the tensions between our classical understanding and the profound implications of quantum mechanics. The journey has also led us to question the very nature of reality and our role as observers shaping the universe. The story of quantum mechanics is not just about understanding the universe, it's about transforming it. It is a tale of relentless scientific curiosity, groundbreaking discoveries, and the transformative potential of fundamental physics. It's a story that has been told over decades, with the story continuing to be built even today. As scientists continue to develop new technologies and expand the reach of our understanding, we can only imagine the wonderful and awe-inspiring wonders that the future may hold. As you now conclude this journey, reflect on the ways in which quantum mechanics has altered your view of reality technology and the universe itself. What questions remain, and what future explorations might you undertake? You now stand at the threshold, having journeyed through the intricate and often bewildering landscape of quantum mechanics. Your exploration has taken you from the familiar world of everyday objects to the strange probabilistic dance of subatomic particles, unveiling a universe far more profound and interconnected than classical physics ever conceived. This is not an ending, but an invitation. The quantum frontier awaits your continued curiosity. Recall the very foundation of our quest, the startling realization that at the smallest scales, particles defy our intuitive grasp of singular existence. You encountered superposition, the astonishing capability of a quantum entity to inhabit multiple states simultaneously, like a ghost in countless places at once, until the very act of observation compels it into a single definite reality. This fundamental role of observation, which we've delved into repeatedly, from the perplexing behavior of electrons in the double-slit experiment to the thought-provoking paradox of Schrodinger's cat, forever blurs the line between observer and observed. It asks us to reconsider if reality is truly independent of our interaction with it, a philosophical inquiry that continues to fuel intense debate among scientists and thinkers alike. Einstein's famous dismissal of the spooky action at a distance for quantum entanglement, though rooted in his profound belief in local realism, ultimately sparked decades of rigorous experimental validation that definitively proved the instantaneous correlation between entangled particles regardless of the vast cosmic distances separating them. This intrinsic link, revealing a unified quantum system rather than merely two separate entities, stands as one of the most profound revelations of the quantum age. Yet this intellectual odyssey has not been confined to abstract theories. You've witnessed how these once esoteric concepts are not merely academic curiosities, but the very engine driving much of our modern technological landscape and shaping its future. From the coherent beams of lasers that revolutionize everything from barcode scanners to precision surgery, a direct application of stimulated emission to the miniaturized transistors within your smartphone, whose operation hinges on the quantum phenomenon of electron tunneling and discrete energy levels. Quantum mechanics is woven into the fabric of your daily life. The ability of MRI technology to peer non-invasively into the human body, providing invaluable diagnostic insights, relies entirely on manipulating the quantum spins of atomic nuclei within powerful magnetic fields. These are not just gadgets. They are testament to humanity's capacity to harness the universe's weirdest rulebook. Beyond these established marvels, you've glimpsed the burgeoning quantum frontier, a landscape bristling with transformative potential. Quantum key distribution, QKD, stands as a bulwark against future threats, offering the promise of unbreakable communication networks secured by the fundamental laws of physics, where any attempt at eavesdropping leaves an undeniable trace. Quantum computing, leveraging the exponential power of qubits and their entangled states, is poised to unlock solutions to problems currently intractable for even the most powerful classical supercomputers, from accelerating drug discovery and personalized medicine, by simulating complex molecular interactions with unprecedented accuracy, to optimizing global energy grids for greater efficiency and sustainability. Furthermore, the fields of quantum sensing and quantum materials promise to usher in an era of ultra-precise measurements and designer substances with revolutionary properties pushing the boundaries of what is technologically possible. The rapid pace of discovery and the substantial global investment in these quantum technologies underscore the profound impact they are set to have on society. The greatest challenge, and perhaps the greatest gift of quantum physics, is its demand for a shift in perspective. It asks us to embrace the counterintuitive, to accept that reality at its most fundamental level is probabilistic, a tapestry of possibilities, rather than a fixed, deterministic sequence of events. This embrace of uncertainty is not a capitulation to chaos, but an expansion of understanding, a recognition that our classical intuition, honed by the macroscopic world, is insufficient to grasp the universe in its entirety. It urges a humility in the face of nature's complexity and an unwavering intellectual curiosity to probe deeper, to continually question, and to seek new frameworks that can reconcile these paradoxes. As we integrate these powerful new tools into our lives, it also places a significant responsibility upon us to ensure their ethical development and deployment, safeguarding privacy, fostering equitable access, and steering humanity towards a future of innovation and progress. The quantum realm is not a distant abstract concept. It is the universal language of physics, the fundamental framework underlying chemistry, materials, science, the forces of nature, and even the intricate processes of life itself. It is a testament to the human spirit of inquiry, a vibrant, ongoing story of discovery that continues to unfold. Your journey through these pages has been but an introduction, an open-ended invitation to remain a participant in this grand scientific narrative. The questions it raises are profound, the technologies it inspires are revolutionary, and the mysteries it unveils are boundless. So keep your mind open, your curiosity ignited, and your sense of wonder alive. For the quantum frontier awaits, and the journey of discovery and truth never truly ends. What personal insights or questions will you carry forward from this exploration, and how might they inspire your own continued engagement with the unfolding wonders of the quantum universe? Ah, what an extraordinary odyssey we've shared, peeling back the layers of reality to reveal the intricate, mind-bending canvas of the quantum world. From particles existing in multiple places at once to the profound power of observation shaping reality itself, our classical intuitions have been stretched, challenged, and ultimately expanded. It was a journey into paradox where even the greatest scientific minds like Einstein grappled with the spooky action of entanglement. Yet through every perplexing turn, we found not chaos, but a deeper, more wondrous order, a cosmic ballet danced by the smallest constituents of existence. This narrative has truly been a testament to the universe's boundless capacity for surprise and our own insatiable hunger to understand it. This relentless pursuit of knowledge, this journey into the grand narratives of science, is the very heartbeat of Astro Horizons. If the unveiling of quantum mechanics has ignited your curiosity and left you yearning for more cosmic revelations, then I invite you to join our growing community of explorers. Your support helps us continue to translate the universe's most complex stories into captivating adventures of discovery. Until we meet again on another horizon, I wish you clear skies, the joy of boundless discovery in every corner of your world, and peace and happiness for you and your loved ones. Stay curious, stay inspired,